Welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll evaluate the performance of a single GPU on the A-100 nodes. We'll measure its efficiency in matrix multiplication, presented in gigaflops per second, utilizing OpenACC directives. We'll conduct these tests using a batch job instead of an interactive job. I've prepared a job script, and in the initial lines, you'll notice many of the variables from our interactive job setup script. The partition option secures that our job will be executed on the A100 nodes. We configure the OpenACC environment variable to gather data on accelerator kernel timing. It's advisable to incorporate error handling configurations into the job script. We also need to ensure that we load the latest Nvidia HPC software, including the Nvidia Fortran compiler. As the A100 operates on a distinct architecture, we need to switch to an environment compatible with the AMD architecture. Lastly, we execute our testing GPU Python script, redirecting its output to a file named output A-100. Additionally, we'll modify the matrix dimension to 32,768 in the Fortran program labeled with file ending 2. The OpenACC directive kernels are used to offload the matrix multiplication to the GPU or the device. Ensure that the Python script specifies the A100, utilizes OpenACC for offloading, sets the file ending to 2, and disables monitoring. We'll adjust the dimension to 32,768 to ensure precise performance assessment, and we'll execute the program once. Keep in mind that the billing factor for the A100 nodes is set at 8. We submit the job script using the sbatch command, which assigns it the job number 10778459. Upon first inspection, the command reveals that the job has been running for 14 seconds. Upon subsequent checks, we confirm that the job has completed. For further details on job scripts, you can refer to the online documentation. Additionally, you have the option to utilize a job script generator available there. For detailed guidance on creating job scripts and scheduling tasks, you can access comprehensive tutorials in the HPC onboarding videos available on this YouTube channel. These videos offer step-by-step instructions and practical examples to help you effectively utilize job scripts for your computing needs. We can check the output A100 file using the Emacs editor. There, we find that the wall time is approximately 58 seconds, with a measured performance of about 150 gigaflops per second based on CPU time. This data comes from the Python script. Optimization details from the compiler and kernel timing data are stored elsewhere. Once our batch job completes, a file will be generated in the directory where the job script was launched. This file will start with slurm, followed by the job number, and end with .out. We can open this file using Emacs and examine its contents. The first output is generated by the module swap command, which we employed to switch to an environment compatible with the AMD architecture. The subsequent output contains optimization information from the compiler. This information mirrors what was generated when we executed the program on the A-100 P100 nodes. As we scroll down the file, we come across several warnings and notes from the compiler. We can remove these warnings and notes to enhance clarity. Referring to the optimization details, we see that the compiler has applied a loop gang vector of 4 to the outermost J loop. For the innermost I loop, the compiler has used a loop gang vector of 32. Following the optimization information, we encounter the accelerator kernel timing data produced by the environmental variable NV compiler ACC time. The computation time for the matrix multiplication on the GPU was approximately 51 seconds. The data region was accessed twice. The time taken for data transfer of matrices A and B and C to the device using the copy-in operation was roughly 1 second. Additionally, the transfer time of matrix C from the device to the host using the copy-out operation was about 330 milliseconds. Looking through the file, we find details about our CPU billing and queue wait time. Although we initially requested a 10-minute wall time, our job concluded in approximately 67 seconds. It's worth noting that our job didn't endure a lengthy wait in the queue as we opted for the development queue. Given that the Fortran program itself took around 58 seconds, the additional time was devoted to executing the Python script, which also includes the compilation of the Fortran program. Towards the end of the slurm file, we find memory statistics indicating that we requested 26 gigabytes and utilized 24 gigabytes. Additionally, the completion time of the job is clearly indicated. We noticed that the compiler automatically set the loop gang vector size to 4 and 32, but we can adjust it manually. We can set the loop gang vector size to 16 for both the J and I loops. This change is made in the Fortran program with file ending 5. Let's test this program to see if it improves performance. First, we need to update the file ending in the testing script while keeping the settings for the A-100 GPU and OpenACC offloading. The matrix dimension remains at 32,768 and the billing factor is still 8. In our job script, we won't redirect the output from the GPU testing script to a file, so the output will go to the slurm file. To submit the job to the slurm workload manager, we use the sbatch command, which assigns the job number 11815560. By using the sq command, we see that the job has been computing for 6 seconds. After some time, we use the sq command again and observe that the job has completed. To check if the job has generated the slurm output file, we use the ll command and confirm the file with job number 11815560 is there. We can then view the slurm output file using the Emacs editor. The first output comes from the module swap command, which we use to switch to an environment compatible with the AMD architecture. The next output includes optimization information from the compiler. As we scroll down, we see several warnings and notes from the compiler, which we can remove for clarity. The optimization details show that the compiler applied a loop gang vector of 16 to both loops as specified in the program. Following the optimization information, we find the accelerator kernel timing data produced by the OpenACC environmental variable NV compiler ACC time. The matrix multiplication on the GPU took approximately 44 seconds. The data region was accessed twice, with data transfer times for matrices A, B, and C to the device, copy in, taking about 1 second, and matrix C transfer from the device to the host, copy out, taking about 336 milliseconds. The outputs from the testing script are now in the Slurm output file. The testing script outputs the compilation command, and then the performance data. The wall time is approximately 52 seconds. The CPU-based performance is about 170 gigaflops per second, which is higher than our initial test performance. We can summarize the results of our two tests in a table. The first test, with a loop gang vector size of 32 for the I loop and 4 for the J loop, had a wall time of about 58 seconds, displayed in blue. The second test, with a loop gang vector size of 16 for both loops, had a wall time of about 52 seconds, shown in green. Next, we will conduct tests with different loop gang vector sizes, and from the table, we see that the best performance was achieved with loop gang vector sizes of 8 on the J loop and 32 on the I loop, displayed in red. You can find additional examples of GPU offloading in the code development and tutorials section of the online documentation. Once you navigate to the code development and tutorials section, you can select the GPU programming model subsection to access more examples and explanations of GPU offloading. In our upcoming video, we'll explore parallel computing on CPU cores, specifically focusing on OpenMP, Open Multiprocessing. OpenMP facilitates the development of programs that utilize multiple cores simultaneously, leading to faster execution. It is compatible with programming languages like C, Fortran, and C++. Through OpenMP, writing parallel code becomes more straightforward and improves performance on multi-core processors. I am looking forward to the next video, wishing you all happy computing in the meantime.